Here we are talking about aromaticity some more. In the previous video, I talked to you about how you derive the Huckel molecular orbitals for the pi system of electrons in the ring. And not only that, but I also mentioned to you that the population, the full population of the lowest molecular orbitals, the ones that fall below the middle line of the Huckel circle, tells you how many electrons your cyclic system needs to have if it's to be aromatic. So what I'm going to show you right now is like the actual charges that these cyclic systems actually do have, and that you see very often in the chemical community. All right, so we're going to start with the three-member ring, which we said that for this to work out, via the 4n+2 sequence, we want n to be 0, or in other words, we only want 2 pi electrons. So that's why I'm depicting this with a plus charge, just cationic, basically, right? And if you kind of think about the molecules, without breaking the octet rule, right? A three-member ring that only has 2 pi electrons will be basically derived from cyclopropene. But cyclopropene does have an sp3 hybridized, or technically a pseudo sp3 hybridized carbon center, which technically disrupts the polyconjugation of the system. So what you have to do basically is remove one of those hydride bonds for two reasons. One, to make this cationic, but also to end up creating polyconjugation throughout the entire ring. Kind of going along those lines, right? The four-member ring, we want a total of 6 electrons, right? So not only the 4 that we get from the 4 carbons, but 2 more to make this aromatic, right? So 2 pi electrons, 6 pi electrons, 10 pi electrons. That's what we're looking for. But the four-member ring, the closest thing we can get to it, just in the neutral sense, is cyclobutadiene. And cyclobutadiene only has 4 pi electrons, right? So one thing you would like to do is add electrons, literally artificially, to get to this point. Now, the 5-member ring, same kind of a similar idea. We could start with cyclopentadiene, but then in one of those instances, the 5th carbon will have 2 hydrogens, which means that this carbon is sp3 hybridized and is breaking the conjugation. For benzene, as I mentioned in the previous video, that's the only instance when you actually have the correct number of carbons making up the ring as the actual value of pi electrons that you need for this to be aromatic. So that's the one that's neutral, and nothing to be done to actually change it. For the 7-member ring, if you go around the ring, what you'll see is that you can put up to 3 double bonds in that ring system. By the 7th one, you'll have to end up with an sp3 hybridized carbon for it to be neutral and have the octet rule, followed. And then for the 8-member system, you could have up to 8 pi electrons. All right, so this is kind of like the entry point, if you will. Like if you are trying to make these things aromatic, you start with a neutral molecule, and these are the neutral versions of each one of those molecules. So you have to do, with the exception of benzene, you have to do something to these molecules just to get them into the aromatic, in the aromatic situation. All right, so I mentioned one of them already. Basically here, you got to remove not just the H, but you got to remove the H and the electrons that come without bonds. So you're removing a hydride, not a proton, not a hydrogen atom. You're removing a hydride, which means the H and the 2 electrons are bye-bye. And there's ways to make that happen. There are reagents that will do this. And what I kind of want to show you is for you to appreciate, like the beauty of these things is that, you could remove hydride reagents with certain carbocations. One of the common ones is triphenyl methyl carbocation. That seems to be a good one to do this type of abstractions with. But if you also think about it, the removal of the hydride creates aromaticity in the ring, which actually gives you a lot of stability. So this has an incentive to make this happen. So it's not going to be as drastic as you might think it would be compared to other non-aromatic molecules. And what you see right here is an example of when you can make these things. Because granted, this will be cationic, so it's not the most stable thing around. For one, you have a carbon that only has 6 electrons, and it's technically carbocation, right? So it's not going to be the most stable thing by itself, but you can make it somewhat stable by utilizing other elements and metals. And this example I thought was very beautiful. This is work done by Alcarazo back in 2011, and it's basically a phosphine molecule where you basically have replaced the regular carbons like methyls or hydrogens with this cyclo cyclopropenium cation. So technically speaking, this phosphine molecule has 3 of those cyclopropenium cations. And it's not shown here in the picture, but there is anions. And I think they were like bromide anions that were, basically canceling out the charge. And then here, the molecule is basically treated because it's still a phosphine, so it reacts with metals like platinum. So it reacts with it to form this beautiful square planar structure on platinum. And then not only that, right, but because now you're introducing this extra bulk from the 3 chlorines bound to the platinum, the molecule kind of also around phosphorus achieves this pseudo square planar shape of its own. So I thought this was a beautiful example of it. It's like, whoa, this is really cool. And yes, in this structure there's also an anion that's not coordinated to anything, that's there canceling out the positive charges, making the whole molecule neutral at the end of the day. All right, now for the 4-member ring, here we want to end up with a 2 minus charge. So the way that you do that, practically speaking, is to basically bring the molecule in question into contact with an alkali metal. And I'm not talking about like potassium from potassium chloride. I'm talking about elemental potassium, like potassium that hasn't lost its 1s electron yet. So you basically take 2 equivalents of potassium in the presence of your cyclobutadiene, and that will actually pump the 2 electrons into the pi system and will create this cyclobutadiene anion version of it. And you might think that's kind of nuts. First of all, just taking the alkali metal to dump the electrons on the system sounds kind of nuts. But once again, you can stabilize this dianionic system if you combine them with metals that have positive charge. And there are some, beautiful examples. These are 2 that I caught, online. So this is work by Kudinov, published in Organometallics in 2016. Basically, if you look at the molecule, you have the 4-member ring right here, and as you can see, it is flat as it can be. Top hat, for rhodium, and rhodium is basically stabilizing the molecule with its charge. If I'm not mistaken, I think that's probably rhodium 3 plus, perhaps. And then right here we see another example. This is by Rominger, also published in Organometallics, where you see the 4-member ring, flat, but it's dianionic and stabilized by the positive charge of this cobalt. And just judging by what we have here, it looks like this might be cobalt 3. Okay, and then there's a bunch of nitrates there, but the important thing is the 4-member ring that's flat and aromatic as well. Oh, and by the way, notice this: the interaction of the metal with the aromatic ring happens equally, distance-wise from all the carbons that make up that ring. So usually we used to pick that as, the interaction happening through the middle because it's equally interacting with all 4 of those carbons. All right, the next one, which is perhaps one of the more well-known examples of aromaticity, aside from benzene, is the case of cyclobutadiene. This molecule basically just wants to have 1 extra electron to end up being aromatic, right? It has technically 5 from the 5 carbons. So all you need to do is remove a proton. If you do that, the 2 electrons that used to be part of this carbon H bond will be left behind as the set of 2 electrons to complete this as a 6 pi electron system. But these electrons didn't come from an external source. They were already part of the carbon, the fifth carbon of the cyclobutadiene chain. Only that one of those electrons exclusively came from hydrogen, right? So the moment you remove a proton, you left the electron that belonged to hydrogen altogether. That's where the negative charge comes from. But now that will give you a system that is 6 pi electrons in total. And this situation where you're gaining stability through aromatization is so good a situation that for a carbon H bond, and even in this case, right, which you could make the argument, okay, technically this is an allylic CH, which is got lower pKa's than just your regular alkane. But even then, like we will be talking about at best, maybe a pK of 40, this one has a pK of 19. And that's a humongous drop on the pK of a CH bond. And it's all due because the moment you remove that proton, this becomes fully aromatic. So the incentive of this molecule to want to be aromatic is more than enough to say the heck with this proton. And that explains why the pK is so low. And granted, this is not the lowest pK. I'm not trying to say that this is like a strong acid, not by a long shot, but compared to other carbon H bonds, it's really acidic. Okay, now benzene. We're gonna get to that, but I just want to show you two examples of the situation where you deprotonate cyclopentadiene. This gets you to the cyclopentadienyl anion. And like the other examples, if you have an anionic charge, one way to stabilize it is to bind it to metals that have positive charge. The oldest example is probably ferrocene, shown right here. And this was particular work done, theoretical work done by Chandler in 2016. But the molecules have been known for a long time, since the 1950s when they were first made. And this is actually some people will argue that probably a platinum complex preceding ferrocene is the true grandfather of organometallic chemistry, but this one is perhaps the better known, and it definitely opened the doors for organometallic chemistry at that point. Here you can see it again, the 5-member ring, totally flat, sandwiching the metal center, fully aromatic. This is iron 2 plus, and basically cancels out the charges of the two cyclopentadienyl rings. All right, and then benzene, we already said it's aromatic on its own, so there's no need to add charge or remove charge. And just like the other examples, you might say, well, you have these aromatic rings that are kind of like binding to metal, getting sandwiched, by metals. And that is no different with benzene itself. You can actually have situations, specifically if the metal has low charge or no charge at all. Like in the case of this molybdenum fragment, they can actually serve as kind of like literally buns, that enclose the metal. And yeah, it's kind of beautiful to see these things. But yeah, so this aromatic characteristic is definitely a thing, even for benzene. All right, so we're almost done. Let's talk about the hydride abstraction of the 7-member ring. Here, same as the 3-member ring, we want to remove a hydride, not a proton. We want to remove a hydride because we want to end up with a carbocation right at this position. And that has two effects. One, it gives you an empty p orbital that completes the conjugation of the 7-member ring. But two, by removing the electrons along with the hydrogen, you end up with a total of 6 pi electrons in this system, which is what makes it aromatic. But that would also mean that this has got a positive charge. And this thing is also pretty well known in chemistry. This actually has a regular name. This is called the tropylium cation. And much like the benzene, the 5-member rings, 4-member rings, you could absolutely use the tropylium cation to bind to metals. It's kind of a beautiful take on it. And of course, you have to have other anions to ultimately counteract the charge, the positive charge of the tropylium cation. But that's where these oxygens kick in. You got a bunch of, you have like a -6 charge from those oxygens, a -1 charge from your cyclopentadienols. So you're talking about -8 in total. So between the 3 rutheniums and the 1 iron, you can totally come up with proper charges that will cancel out the 8- collective charge of this thing. But I think this is beautiful, right? You have the octahedral shape for the iron. You have this Decker compounds, the sandwich compounds with ruthenium, and even right here. I mean, just looking at these structural features that you can generate with these things. I don't know about you, but this is the kind of thing that like drove me to chemistry. Like this is just beautiful. It's just, it's just what one old former professor of mine used to say. These are sexy molecules. You know, I don't know if you feel that way, but yeah, I think they're cool. All right, and then the last one, the eight-member ring. You have eight electrons, but you want to end up with 10, so you have to add two electrons to this, just like what we did for the four-member ring. And this is the more common version of making this thing aromatic. So the cyclooctatetraenol anion is actually pretty well known in organometallic chemistry. And as you can see in this picture right here, this well, it's not really a picture. This is the actual experimental structure of the molecule. You can see that that A-member ring is totally flat, and it's got a 2- charge, hence the presence of two potassium cations in this molecule. So this is just beautiful, beautiful work. And then this is one of the ones that I might have mentioned to you in the past. The creation of a sandwich compound with big cations like plutonium. So this is just oh, it's beautiful, right? It's work by Maran in 2017 in Angivanta. Yeah, just beautiful work. So this is just kind of to give you an idea of how you make these things, what you can do with them. But the video has been long enough, and I can continue ranting about the beauty of these molecules, but we have things to still cover. So in the next video, we will talk about the difference between aromaticity, anti-aromaticity, and non-aromaticity. So see you then.